So now that we know that matrix exponentials can be used to solve systems of ordinary differential equations, it's worth remembering that we could run into a sort of snag here because we've already encountered situations where we have a perfectly fine matrix with real entries, but its eigenvalues may be non-real numbers. So what in the world would we do if when we diagonalize our matrix, the diagonal entries of D have non-real numbers in them? Well, what we need to do is we need a formula for e raised to a non-real number, a complex number of the form a plus bi. And there's a theorem called Euler's formula, which tells us exactly how to express e to the a plus bi as a complex number. So let's walk through the calculation here. So the first step here, if we want to calculate e to the a plus bi, is to recognize that this is the same thing as e to the a multiplied by e to the bi. The next thing to do is to recognize that, well, e to the a is just some real number, e to the a, so I can keep that. But what is e to the bi? So what does it mean to raise e to a purely imaginary number? Well, what we could do is we could apply the Taylor series formula. The Taylor series formula for e to the bi would be the sum from k equals 0 to infinity of 1 over k factorial multiplied by b to the k multiplied by I to the k. So now we want to have a better understanding of what this infinite series looks like. And I think that the best way to do this is to separate the series out by keeping track of the even k's in one series and the odd k's in another series. So here we're summing through all k's from 0 to infinity. What I'm doing is I'm breaking this apart in terms of the even and the odd k's. Now, the reason for doing this is because we can elegantly write formulas for even and odd numbers. If I want to cycle through all even k's from 0 to infinity, what I can do is I can replace each of the k's in the sum end here with 2 times k, and then cycle through all k's from 0 to infinity. So this would give me all even numbers from 0 to infinity. And the same goes for odd numbers, except instead of replacing my k's here with 2 times k, I can replace my k's here with 2k plus 1. And then if I cycle through all k's equals 0 to infinity, this would capture all of the odd numbers from 0 to infinity. And now when I take a close look at these two terms, the annoying parts here are the i's. But in this first part, if I'm looking at I to the 2k for all values of k, this is the same thing as I squared multiplied by k, but I squared is negative 1. So now the even parts here simplify from 1 over 2k factorial times b to the 2k times I to the 2k to negative 1 to the k, that takes care of this I to the 2k, divided by 2k factorial multiplied by b to the 2k. What about the odd terms over here? Well, again, the hard part is the I to the 2k plus 1. Well, I to the 2k plus 1 is the same as I multiplied by I to the 2k. And we already saw that I to the 2k is the same thing as negative 1 to the k. So this all simplifies to negative 1 to the 2k plus 1. So I'm missing an I over here, so I should fix that in the notes. I'll do that. And when all is said and done, this entire expression ends up simplifying, if we look at our old Taylor series formulas, to this, this expression capturing all of the even values here. This is cosine of b. And this expression over here, where again I've left out my I, is I times sine b. So this is a famous formula. This is called Euler's formula. And this says that e to the a plus bi is always e to the a multiplied by e to the bi. And when we apply these Taylor series arguments, we end up simplifying to e to the a multiplied by the quantity cosine of b plus I times sine b. So e to the a plus bi is e to the a multiplied by cosine of b plus I times sine of b. And once we have the famous Euler's formula, we get two important consequences. So what if I looked at, therefore, e to the a minus bi? Well, according to Euler's formula, this is the same thing as e to the a multiplied by the cosine of negative b plus I times sine of negative b. If we remember our properties of sine and cosine, cosine is what's called an even function, which means that cosine of negative b is the same thing as cosine of b. So this simplifies from cosine of negative b just to cosine of b. And then sine is an odd function, which means sine of negative b is negative I times sine of b here. So e to the a minus bi is e to the a multiplied by cosine of b minus I times sine of b. And we also get a famous identity called Euler's identity. If I plug in a equals 0 and b equals pi, and then I took e to that number, I would be looking at e to the I pi. This would be e to the 0, that's a, multiplied by cosine of b, which is pi, plus I times sine of b, which is pi here. Well, sine of pi is 0, and cosine of pi is negative 1. So this gives this famous formula, e to the I pi equals negative 1. So we have the Euler's formula, which says e to the a plus bi is e to the a multiplied by the quantity cosine of b plus I times sine of b. And then from that, we get this parity formula, e to the negative, or a minus bi is e to the a multiplied by the quantity cosine of b minus I times sine of b. And then from that follows the famous Euler's identity, which is e to the I pi equals negative 1. So how might this come into play with an example? Well, let's say that we were trying to solve a system of ordinary differential equations, and perhaps our coefficient matrix is this matrix A here, whose columns are 1, 1, and then negative 1, 1. Well, I diagonalized this matrix earlier, and I got complex or non-real eigenvalues. The eigenvalues were 1 plus I and 1 minus I. So when I did my diagonalization here, I needed to use non-real numbers. So even though my matrix A has real numbers, the eigenvalues are not real numbers. But that's okay because there's nothing stopping me from applying a matrix exponential here. If I take my matrix exponential, I can solve my initial value problem, u prime equals a times u. And here I'm choosing the initial vector u sub 0 to be the vector 0, 2. Now, what does this look like? This should end up being, let's put it all up here, x times the exponential of d times t multiplied by x inverse multiplied by u 0. So the x inverse and u sub 0 are coming from the diagonalization that I started with here, and the u sub 0 is something supplied to me from my initial value problem. So the only thing I really need to do here is I need to figure out the exponential of d times t. So that would be the diagonal matrix, whose diagonal entries are e to the 1 plus I multiplied by t, and then e to the 1 minus I multiplied by t. If I apply Euler's formula, this would be e to the t multiplied by cosine of t plus I times sine of t. And then the second entry in the diagonal would be e to the t multiplied by cosine of t minus I times sine of t. So in the exponential of dt, we have these imaginary numbers floating around. But the idea is that when I multiply by x and x inverse, which themselves have i's in them, and then multiply by u0 here, I get my coordinates of my solution vector. And when I did that simplification earlier, I got the coordinates of u of t as negative 2 sine t and 2 times cosine t. So in the solution to this initial value problem, the two coordinates are negative 2 sine t and 2 times cosine t. So we were able to use matrix exponentials to do this. This is an interesting problem because even though the coefficient matrix A here has all real numbers in it, its eigenvalues are not real numbers. And so its matrix exponential requires us to work with Euler's formula here.